Hello everyone, and welcome back to the series on complex variables. Today we're going to be continuing our exploration of differentiability of functions in the complex plane and talk about a property that is unique to complex variable functions known as the analytic property for those functions. So let's just go over some of the basics that you definitely should know before diving into the realm of analytic functions. So what does it mean for a function to be differentiable at a point z? Well, this limit has to exist from all possible directions, because keep in mind, h, the thing that's going to 0, can be decomposed into hx plus I hy. So when you approach 0, it shouldn't matter the direction that you approach it. You should get the same exact answer. If you get the same exact answer from all directions, then we say the limit exists, and the function is differentiable at that particular point. Also, let's assume that f has a real imaginary decomposition of u plus iv. Then, if you differentiate u with respect to x and v with respect to y, and they match at a particular point z equals x plus iy, and also uy being equal to minus vx also satisfying each other, and these equations are again referred to as the Cauchy-Riemann equations, then that implies that it's differentiable there. Or if f is differentiable at that point, then the Cauchy-Riemanns will exist there. Now, it doesn't necessarily go the other way around. You have to require continuity of its partial derivatives. So if the Cauchy-Riemann equations hold, and ux, uy, vx, and vy are all continuous, then f prime exists, implying that f is differentiable at that point. So this gives us a quasi if and only if criteria for differentiability of a function. Differentiability implying Cauchy-Riemann, and Cauchy-Riemann and continuity implying differentiability. Let's look at a computational example to see if you understand these particular ideas. So let's assume that f of z is equal to the conjugate of z squared. So what is the conjugate of z? Well, that's going to be x minus iy, the quantity squared, which will come out to x squared plus y squared, and then plus minus 2xy I. So there's our u, and there's our v, and we should be able to analyze the Cauchy-Riemann equations once we have our Ri decomposition for it. So what are we going to have? So ux will be equal to 2x, and then uy will be equal to 2y. So those are quite easy. And then vy will be equal to minus 2x, and minus vx will be equal to minus 2y, which will be equal to 2y. Right? So are they all continuous? Yes, they are all continuous. So they're all continuous. So that's a good sign for differentiability. Now notice that ux and vy are only equal to each other if and only if x is equal to 0. Right? But notice that these are true for all z and c. Right? So the only case where this function will be differentiable will be when x is equal to 0. Right? So when is that going to be, where is that going to be located? So if we were to draw our complex plane, let's assume that this is the real part of z, and this is the imaginary part of z. So where is this function differentiable? So it's only differentiable if x is equal to 0. So that's only on this line. Right? So this is the location or the set of points. F is differentiable. Right? Now, if I were to ask you, is it smooth at the origin, or is it smooth at the point I, or is it smooth at the point negative 4i? Most people will say, well, doesn't differentiability imply smoothness? Well, not necessarily, because usually when we think of smoothness, we usually want to draw some open neighborhood around the point and see if it's pretty much differentiable at all points in that neighborhood. Right? So if I were to draw an open circle at any point on this line, notice that I cannot find an open neighborhood that's not just a point, that is, it has to have a radius of 0, that has points that are differentiable at all points in that set. So let's just make formal notes of those comments. So f is differentiable only when x is equal to 0, not in an open region around those particular points, right? So if that is the case, then we can say that f is not smooth around those points. And in particular, since differentiability does not really give us the idea of smoothness that we want, that means differentiability is not enough for smoothness. Smoothness in C. Smoothness in C. Smoothness in C. All right? So that motivates the existence of the next very important class of functions. So we say that f is analytic at some point z0 in C if there exists a real number, epsilon, greater than 0, such that f is differentiable. F is differentiable for all z within that neighborhood of that particular point. Right? So that means fz, which is z bar squared, is differentiable only when x is equal to 0, but it is not analytic on x is equal to 0. And why is that the case? Well, if x is equal to 0, that means y is a free variable. So that means the set of all points on this particular set S is of the form z, where z is equal to iy, where y is a real number. But if we were to draw a vertical line centered at some particular point iy, and draw a circle around it, notice that there's going to be some points inside of that neighborhood that have a real part that is non-zero, right? So such an epsilon doesn't exist for that particular point. So although it is differentiable along that particular line, we have that f is analytic nowhere. Because in order to be analytic, you have to be differentiable. In particular, you have to be differentiable on an open set surrounding those particular points for which you claim to be differentiable at. All right? So let's look at another example, a little bit more involved. So let's assume that f of z is equal to the principal branch of the natural log function. So what is the principal branch of the natural log function equal to? So that's going to be equal to the natural log of the magnitude of z plus I times the argument of z. So is this function differentiable? And if it is differentiable somewhere, is it analytic there? So what is the magnitude of z equal to? Well, that's going to be equal to the natural log of x squared plus y squared. And then we're going to have I times the arctangent of y over x. And then we can make this a little bit more nicer, write that as 1/2 times the natural log of 0 of x squared plus y squared, and then plus I times the arctangent of y over x. So what's the point of doing this? Well, this gives us the real imaginary decomposition of our particular function. There's our u, and there's our v. Now we can see if the Cauchy-Riemann equations hold, because if the Cauchy-Riemann equations don't hold, then it's definitely not going to be differentiable and hence not analytic at those particular points. So let's take the partial derivatives of these and see what we get. So the partial derivative of u with respect to x is going to be equal to 1/2 of, so if we take u with respect to x, that's going to give us 2x divided by x squared plus y squared on the bottom. Which we can just simplify to be x divided by x squared plus y squared. And then if we look at Vy, that's going to be equal to what? So that's going to be 1 over 1 plus y over x, the quantity squared, and then times the derivative of that with respect to y. So that's going to be equal to 1 over x. So what is this going to be? So that's going to be 1 over x times 1 plus y squared over x squared. And let's just multiply, what do I want to multiply this by? Maybe by x, top and bottom. That's going to give us x divided by x squared plus y squared. And then notice that ux and vy will now be equal to each other. So that's great. But just because ux equals vy does not mean the other Cauchy-Riemann equation is going to hold. So let's check that out just to make sure. All right, so this is a good sign. So let's check out the other. So ux, say vy. So vy is going to be equal to, uvy is going to be equal to, what was that? Oh, that was vy. So ux equals vy, and uy, let's do uy. uy. So uy will be equal to, so what is u? So it's actually going to be the same exact thing, right? So u1/2, the only difference, instead of 2x on top, we're going to have 2y, and then x squared plus y squared, which is going to be equal to y all over x squared plus y squared, and then minus vx is going to be equal to 1 over 1 plus y over x, the quantity squared, and then times the derivative of the inside with respect to x, and let's not forget our minus sign. So the derivative with respect to x, that's going to be equal to minus y all over x, the quantity squared, by the chain rule. And then we're going to have what? So we have our minus signs going to cancel. That x squared is going to distribute in, cancel with the bottom, so that's going to give us y all over x squared plus y squared, which will match with that as well. So since ux equals vy and uy equals minus vx, that means Cauchy-Riemann equations hold for all z in C. Right? Also, if you look at these particular functions, these are going to be rational functions that are going to be continuous as long as x, y does not equal to 0, 0. Right? So these are going to be continuous for all z and c with x, y not being equal to 0, 0, or z not being equal to 0. Right? So this means what? So this means that f of z equals the natural log of z is analytic for all z and c except for the origin, which is usually where your branch cuts are going to be located at. Right? So that's actually very, very nice in terms of proving that functions are differentiable and more so analytic. Okay? So what exactly does our region look like? So pretty much the only point that you do not have in the differentiability region is going to be the origin, and that's why we say that it's analytic everywhere on this particular set, because it's differentiable at a point. For example, it's differentiable at this point right here, and you can always draw a neighborhood around it of radius epsilon, and it's always going to have points in there that is not going to be equal to 0, as long as you choose your epsilon small enough. All right? So let's look at another example. Suppose that f is differentiable on, let's call the region R to be equal to the set of all z, such that the absolute value of z is less than or equal to 1. So if f is differentiable on this particular set, what can we say about the analyticity or the potential analyticity of this particular function? Right? So if we draw a little circle around it, so the norm, less than or equal to 1, so if that's 1, 1, minus 1, and minus 1, then this is the set of all points for which it is differentiable. So is it analytic on this region? Well, if I were to pick this point at 0, there does exist an epsilon that it has points that are differentiable there. Now, We don't necessarily know if those partial derivatives are continuous there, but it's differentiable there. That much we can say from the theories that we've already proven. But notice if I pick this point right here on the boundary, notice that this is not analytic on the boundary, right? But if the function f is, or let's say it has continuous partials on the interior of R, then f is going to be analytic on the interior of R. Big assumption here, if f is continuous or has continuous partials, then f will be analytic on its interior. So that much we can say. And what is the interior? Well, that's going to be the set of all z, such that the absolute value of z is strictly less than or equal to 1, which is the same exact set. The only difference is you don't have the boundary. Right? So that means it's going to be analytic everywhere on the interior of that circle. The next theorem that I want to mention should be quite straightforward. Suppose that R is an open set, and let's assume that f is analytic on all of R. Then the Cauchy-Riemann equations will also hold at all points in R. And why is that going to be the case? Well, if f is analytic on that particular set, that means f is differentiable at all points in that set. That means it shouldn't matter the direction for which you approach in that limit, which means that the function should satisfy the Cauchy-Riemann equations, because that's pretty much how we proved it in the last video. Now the next theorem will seem a bit of a reach, and it says the following. Suppose that f is an analytic function, and let's also assume that f prime is analytic too. Now we will actually show later on that if f is analytic, then that means f prime also is analytic, and then f double prime will be analytic too, and all its derivatives will exist. And this will be a very, very strong theorem, but we're going to prove it in a more elegant way a little bit later on, once we have a couple mechanisms proven in the realm of complex integration. But for now, we'll just take this as an axiomatic basis. In particular, let's assume that f and f prime are both analytic. Then ux, ui, vx, and vy also will be differentiable too, with respect to x and y, and also all higher orders of x and y as well. Right? But let's just assume that these basic facts are indeed true. We'll come back to the proof later. All right? So if f is analytic, then what do we know? Then that means ux must be equal to vy, and also uy must be equal to minus vx. Right? Now, if ux, uy, vx, and vy are differentiable functions, I should be able to differentiate these two expressions with respect to any variables that I want. For example, I should be able to differentiate it with respect to x, given as uxx being equal to vyx, and I should be able to differentiate the second expression with respect to y if I want to, and call it uyy is equal to minus vxy. Right? Now, if vx, vy, ux, uy are continuous, then vxy equals vyx, and uxy will be equal to uyx. You might remember this theorem from the realm of complex variables as Clairaut's theorem. Clairaut's theorem. Right? That is the equality of mixed partial derivatives. Right? So that means vyx and vxy will be equal to one another. So that means I'm going to have these two equations. In particular, uxx will be equal to vxy, and uyy will be equal to minus vxy. And then I can take these two things together and then add them, and then I'm going to have that uxx plus uyy will be equal to 0. You might remember this from the multivariable calculus realm as just the Laplacian of u being equal to 0. And you should be able to prove using a similar strategy that the Laplacian of v will be equal to 0 as well. And then from this, you might have learned this in multivariable calculus, but if not, I'll just define it here. So if f maps R2 to R, and the Laplacian of f is equal to 0 on R, then f is said to be harmonic in R. Said to be harmonic on R. Right? And that need not be the set of real numbers. That could be on any open region as well. Right? So what do we see? So we see that if f is an analytic function, then its real and imaginary parts will be harmonic. So that's actually quite interesting. So theorem 3, let's state it formally. So if f is analytic with f is equal to u plus iv, and also that f prime also analytic, which again I mention only for the fact that we need it for this theorem, but later this actually is going to be, oh, of course f prime is analytic because f is analytic too, but let's of course assume that that's not necessarily true yet, but in this case let's assume. Then both u and v are going to be harmonic on some region R, right? So let's assume that's on R, and let's assume that that's on R as well, right? So every analytic function has real and imaginary parts that are both harmonic functions. Now you might be thinking, well, what's the usefulness of that? This has several different applications in physics and engineering, which we'll get to at a later time. As you may already know, working in the rectangular coordinate system sometimes is not the most easiest to do. For example, if you want to study water flowing through pipes, rectangular coordinates is extremely annoying since you have a bunch of square roots, x squareds, and y squareds, whereas if you want to work in polar coordinates or cylindrical coordinates, it's a lot more easier to deal with because x squared plus y squared is just looking like r squared in the polar coordinate realm. So the natural question is, since everything we've built so far is from the perspective of the rectangular coordinate system, is it possible that we can switch into polar coordinates via, say, z is equal to r to e to the I theta, and give us a equivalent representation for the Cauchy-Riemann equations and also the Laplacian equations for harmonic representations of the real and imaginary parts u and v respectively. So if we change this into r e to the I theta, then we're going to have f of z representable in the form u r theta plus I v r theta. Right, because x is equal to r cosine theta and y is equal to r sine theta, so you can easily represent u and v in terms of r and theta. Right, so once you have this f is equal to u plus iv form, i.e. the real imaginary decomposition in polar form, then one can ask, well, can you represent the Cauchy-Riemann equations in polar form, and can you also represent the Laplacian equation in polar form? So I'll show you how to derive the Cauchy-Riemann equations in polar form, and I'll leave the Laplacian representation for you as well, since it obviously requires the second order derivative twice and a linear combination of derivatives, so sometimes it can get algebraically intensive, but it's a fun exercise nonetheless if you haven't already done so in the past. All right, so once we have our function f of z in this u plus iv form, then how do we find the derivative at a particular point? So I'm going to use the average rate of change perspective because I think it's a little bit more easier to derive with. So that's going to be equal to the limit as z approaches z naught of f of z minus f of z naught all over z minus z naught. So what do we exactly mean by z approaching z naught? Well, if z is approaching z naught, then this is going to take two different directions since z is now decomposed into r and theta. So r is going to approach r naught, and theta is going to approach theta naught, right? So we have those two-dimensional representations. So let's just draw a quick representation of what we exactly mean by r approaching r naught and theta approaching theta naught, just in case you aren't familiar with how limits work in the polar coordinate spectrum. All right, so let's draw our circles here. So what we're going to do is we're going to have our theta naught Let's assume that's there, and let's assume that this is our r naught here. Let's again draw our theta naught here and our r naught there. So our first limit, for example, let's assume that theta is going to approach theta naught, meaning that r will be equal to r naught is going to be a fixed value. And then we're going to have r approaching r naught, meaning theta will be chosen to be a fixed theta naught value. So in the theta approaching theta naught realm, so we're going to approach this angle theta naught from two directions. So theta is going to approach theta naught from, I guess you could say, the left or the clockwise direction, and theta will approach theta naught from the counter clockwise direction. And for our r approaching r naught, so r naught is going to be a real number, so r is going to approach it from the left, and r is also going to approach it from the right hand side as well. So those are the two limits that we're going to be performing in this calculation, right? And keep in mind, it shouldn't matter the direction that we choose. We should get the same exact answer, and that's going to give us our Cauchy-Riemann equations in polar form. Right? So let us write our limit in our I decomposition form. So f prime of z will be equal to the limit as z approaches z naught of u r theta minus u r naught theta naught all over r e I theta minus r naught e to the I theta naught, and then plus I times the limit as z approaches z naught of v r theta minus v r naught theta naught all over r e I theta minus r naught e to the I theta naught. And now we're going to approach these from our two directions that we mentioned before. Right? So our first approach is theta is going to be theta naught, and that's going to be fixed. And then r is going to approach r naught. Right? So theta and theta naught will be the same. That means this e to the I theta, that e to the I theta naught will be both e to the I theta naught, and that can factor out, and you're going to see the same exact thing on the right-hand side as well. So once you perform that substitution, you're going to find that f prime of z will be equal to 1 over e to the I theta naught multiplied by, and then you're just going to have a derivative with respect to r. In particular, you're going to have the derivative of u with respect to r in the first term. And then over here, you're going to still have your I. You're going to have your e to the I theta naught. And then you're going to have your partial derivative of v with respect to r on the right-hand side. Right? So that's going to give us our first statement. And then for the second, r will be equal to a fixed, r is equal to r naught. And then theta will be approaching theta naught. Now you're not going to have directly a definition of derivative because you're going to have an e to the I theta minus e to the I theta naught. Yes, the 1 over r naught is going to factor out. So you're going to perhaps have to use some derivative rules, L'Hopital's rule in particular, possibly. There are a couple ways to do it, in order to get what you want. So obviously we're going to have our 1 over r naught. You probably can imagine that you're going to have an e to the I theta naught that's going to be constant in both of those terms once you differentiate. And then what you're going to be left with is a partial derivative of v with respect to theta. And then over here you're going to have a minus I over r naught e to the I theta naught, and then partial derivative of u with respect to theta. So I highly recommend working out those subtle calculations in that particular representation. Right? But once we have these two expressions, then all we have to do is just equate real and imaginary parts. So for example, this will be equal to this. Notice that both are going to have an e to the I theta naught, so that's not going to be important for us. So what we're going to have is u with respect to r will be equal to 1 over r v with respect to theta. And then our second equation is going to be v with respect to r will be equal to minus 1 over r times u with respect to theta. And that's the Cauchy-Riemann equations in polar form. Right? So it's actually pretty nice. Not as nice as the ux equals vy and uy equals minus vx approach, but to some degree they actually look the same, aside from this 1 over r coefficient that is in both, or 1 over r variable, I guess you could say. Also, if g is harmonic, with G represented in polar coordinates, r and theta, then you should be able to verify that this will be G double r plus 1 over r G single r, and then plus 1 over r squared times G double theta is equal to 0. So this is what we represent as the Laplacian of G in polar form. And obviously you should be able to verify that U and V, once written in polar form, will both satisfy this relation. And I'll leave that as an exercise for you. All right, so those are some of the very important things that you definitely should know when it comes to analytic functions and also the harmonic behavior of the real and imaginary parts of analytic functions. So I hope you enjoyed this video, and I'll see you in the next one. Take care.